Good morning, everybody. Welcome to a sunny, warm morning of Chem 1211 with your host, me, Dr. White. Hopefully, you're all ready for an exciting morning. I am. You can tell I'm all fired up. All right, a couple important things. First of all, let me remind you this Thursday, if you have lab on Thursday, or Friday, if you have lab on Friday, I'll be going through the gas problems and you should work on them before I do, because that will help you get a good grade on test number 3. Speaking of test number 3, hold on 1 second. Actually, it's more than 1 second. I log into Blackboard. Excuse me. Good question, Kelly. Hang in there. 5 more seconds. 4, 3, 2, 1. All right, let's talk about. By the way, all questions are good questions in my class, always. All right, you should have gotten in your email yesterday about 5 p.m. Hopefully you're checking your email. And this was also on Blackboard. Next Wednesday, a week from today, the day right before your taxes are due. If you haven't done it, I'll be working on mine. That's one of the few things in life I really procrastinate. Don't know why, but I do. Tomorrow I'll get it done, which for me is pretty early. All right, next Wednesday, I'll be giving test number 3. I'll do like test 1 and 2. I'll email out at noon, right after our class approximately, the password for test number 3 PDF file. You'll have until Thursday, the following day, 1 p.m. to take test number 3 and upload it as a single PDF file. Remember, all my tests are not open tests, which also means you shouldn't be looking at any videos or talking to anybody. That's cheating, and I will do what's in my syllabus. Now, test number 3 has 9 pages, 20 problems. Some of the problems have multiple parts, and like A, B, and C, and there are 5 multiple choice questions. It will cover gases and solutions, which is chapter 11, chapter 12, and part 1 of chapter 13, which is in the same file as chapter 12. Go look at the title. You'll see I'm not lying. And the point breakdown is there'll be 48 points on gases, 57 on solutions. There's just more I can ask. And it adds up to 105. And you know what that means? There's 5. Does it look like I'm coming right out at towards you? Like almost 3D? Got to put on those special 5. Yes, 5 bonus points. Which one are the bonus points? You pick them. I just had the test add up to 105. I don't like those teachers who at the end put a real impossible, here's your 5-point extra credit. No, it just adds up. That means I can make the whole test hard. No, I don't do that. Ooh, got a question or comment. Novin, you're welcome. And remember, as in test 1 and actually test 2, underneath your name, it will say, please use proper significant figures for all calculated answers. And I think I modified it. Now it says, please use 3 significant figures for all atomic masses. I've posted important information for test number 3 in the lecture folder of Blackboard. You don't have to memorize a lot of the formulas because I've stopped making students do that. Now, I reserve the right to subtract up to 25 points anyone who does not follow instructions or does not upload your tests on time, unless you have some really good excuse that you let me know beforehand or let me know. I'll have like test 1 and 2. There'll be the test file. There'll be 2 versions probably, and a periodic table and my instructions in case you need it. And if you have any questions during the test, I'll be checking my emails, so email me. And Wednesday night, I will have my office hour, just like I will tonight. And therefore, you can always stop by if you have any questions. And on next Wednesday, there will be a normal Zoom lecture. I can get away with that on Zoom. And I'll be posting everything by Sunday, if not earlier. And the Monday after test 3, I will go over the answers like I've done for test 1 and 2. And I also will delete it from the video because I don't want that floating around. And that's test number 3. Anybody have any questions on test number 3? Ooh, my finger's broken. Oh, there it is. Nope, doesn't want to work. Oh no. This one's broken too. Oh no, I gotta get my hands. Oh no, I need new batteries. Oh no, it's totally miserable and awful. Humor Wednesday. Look out. All right, seriously, any questions on test number 3? And if you're not comfortable asking now, always feel free to come to my office hours. All right, let's get back to solutions. Did anybody happen to think of if you open your refrigerator and you saw a bottle of pop in there? You know, that's what other people call soda. That's the solution. Did you happen to think when you inhaled, you were taking in a solution of oxygen, nitrogen? We just happen to call that air. All right, thumbs up, people. Did you see molarity on your screen? Thank you. All right. On Monday, I started talking about one of the ways we can measure and determine concentration of a solution. Concentration, how much of a certain solute is in a given amount of solution. And the most important one for chemists is molarity. And molarity is indicated by a capital M. And molarity by definition, which is very important, see, it even says on the slide that you should know, is moles of solute per 1 liter solution. But in the lab, we usually measure milliliters, and 1 liter equals 1,000 milliliters. Therefore, moles of liter equals moles per 1,000 milliliters, which is molarity. And this everybody get the subtle hint? You should know molarity is moles per 1,000 milliliters. Now, before I get to important questions, let's go to the whiteboard. Oops. And let's take a look at this. Let me make sure. Everybody see my problem on the screen? Thumbs up, people. Thank you. All right. Now the question is, what does 3.778 capital M KBR mean? Well, I'm going to do this one because I want to, and I will. And whenever you see capital M, that means molarity. And what is molarity? Moles of solute per 1,000 milliliters. So what does this mean? It means 3.778 moles of KBr, potassium bromide, per 1,000 milliliters. You could have put down liter, 1 liter, but you should use 1,000. You'll see later this morning. Now, I should remind you, this is an exact number. This is, in this case, for significant figures. Oh, I better share. And for those who haven't figured out my handwriting, let me decode it for you. And number 2, what does 7.92 capital M H2SO4 mean? Your turn. Oh, I see a lot of people have their cameras on. Well, a lot more could turn them on if you'd like to make Dr. White happy. I'll do Jewish guilt. You know, I don't feel that happy if you don't turn on your cameras. I told you it's Miserable Humor Wednesday. It's getting pretty miserable. All right. I think everybody's done. Let's take a look at this. What does 7.92 capital M H2SO4 mean? Ooh, it's serious Wednesday. And capital M, as soon as you see that with a number and a formula, that means molarity. And molarity is moles of solute per 1,000 milliliters. What's the solute? H2SO4, sulfuric acid. So what it really means, 7.92 moles of H2SO4 per 1,000 milliliters. Oh, let's do another one. These are fun and such a beautiful morning. That's better. That's not. All right, time for Dr. White to decode his handwriting. What does 10.7 capital M NaCl bracket AQ close bracket mean? And what is the solvent of this solution? I'm going to let you try this one too. Boy, am I a nice person sharing all the fun. Remember, if you can, turn on your webcam. Makes Dr. White happy.
Hey, Dr. White.
That's me. Yes, Eric.
Question for 1 and 2. Those you just want the meaning, correct? Those we don't have to
Well, all right.
find a solution for that.
Well, Eric and Michelle, that's a great question. When you're taking a test, read the question. All I'm asking is, what does that mean? And what that means, like in 3.778 moles of KBr per 1,000 milliliters. I have nothing about the solvent there. Same thing in number 2. Now, number 3, it says, what does 10.7 capital M NaCl bracket AQ close bracket mean? And it also asks, and what is the solvent of the solution? I remember, I think on test number 2, some of you didn't read the problem or you didn't understand what you were reading. In the case of the second part, you can always email me during a test. But anyways, does that answer your question, Erica Michelle?
Yes, thank you, Dr. White.
You're welcome. And as always, all questions in my world are good questions. But honestly, I don't know the answers to all of them, but chemistry, most of them that you'll ever ask, like all of them, I sure do, or I'll find out. All right, let's take a look at this. What does this mean? As soon as you see capital M, molarity, moles per 1,000 milliliters. So what does it mean? It means 10.7 moles of NaCl, don't forget to pass the NaCl, per 1,000 milliliters. But it asks something else. What's the solvent? And that you see here. AQ in brackets means solvent is water. If you wanted to write out water, W-A-T-E-R, that would work too, because I know both. Aren't you glad you have an instructor that knows chemistry? Now, it turns out molarity is extremely useful to chemists, both in academic labs and industry, like at a chemical plant. How so? Well, it turns out you can make stock solutions. And you can make a bottle, or if you're in a plant, you make, maybe a 500 pounds or 200 gallons. And when you need a certain amount of moles of something, if it's in solution already, you can measure it out very easily. How? Well, first of all, I gotta have some tea. Boy, that's just like Jay's potato chips, except I can't stop drinking it. Oh, that was a good one. One for Dr. White. All right, now let's look at some important molarity questions. How many moles of solute are in X milliliters of a known molar solution? Don't forget, everything you see typed on here, you can get in Blackboard, and everything else, you can go back and look at the video. All right. Everybody see the whiteboard? Thumbs up. Okay. Shake your head, people, too. All right. Now, let me decode it. How many moles of KOH? We'll learn later in chapter 14, which is after chapter 15, what KOH is. It's a base, and I'll teach you what a base is, are in 521 milliliters of a 1.75 capital M KOH solution. Well, how do you do this? Well, you know the first thing Dr. White's going to do. What are we trying to find? Moles of KOH. What are we given? Well, we have 520 milliliters of solution, and we're also given this. As soon as I see the capital M, I know I'm dealing with molarity. So the best thing to do is, what does that really mean? And you know, that's moles per liter. How many? 1.75 moles KOH per 1,000 milliliters. Now, the one thing I really have for sure is this. So I'm going to start out with 521 milliliters. And if I had some sort of conversion ratio, what units do I want my answer in? Well, we figured that out at the beginning. That's moles of KOH. So what do? I use my good buddy, my good friend, unit analysis. No, we're not done with it. Unit analysis is always helpful. And unit analysis is whatever I'm trying to get to goes on top of that ratio. Whatever I'm trying to get rid of goes underneath. Where do I get those numbers? From right here. That I knew capital M, KOH meant moles, molarity, which means I could come up with that ratio, which means I can immediately put it in there. Oh, first of all, moles of KOH, milliliters from unit analysis. Where do I get these numbers? From right here. And it's 1.75 moles of KOH per 1,000 milliliters. Notice milliliters divided by milliliters, anything divided by itself cancels out, becomes the number one, and I'm left with the units I want. Now, just to remind you, this is an exact number. It plays no role in significant figures. So in this case, we have 521, 3 significant figures, 175, and that's 3. So my answer should be 3 significant figures. And now I feel comfortable going to my calculator. First of all, I got to open it up. Next of all, I got to let you see it. And that's the number I get. And I'll let you round that off to 3 significant figures. I'll give you 3 seconds. 1, 2, 2.5, 3. And hopefully you all got 0.912. And that's the answer. And what this helps me is, if I needed 0.912 moles of KOH, I had a stock solution of 1.75 molarity KOH, I'd only have to measure out with a graduated cylinder 521 milliliters. And that's a whole lot easier than weighing it out as a solid and then having to dissolve it in water. most reactions, like all the ones I've ever done, have always been in a solvent where you dissolve solutes reactants in a solvent. And I'm going to be real nice today and say, it's your turn to have some fun. So let me decode this for you in case you haven't figured out my handwriting. And sometimes I even have to decode it for myself, especially when I was taking notes as a college student because I was in a hurry writing. But anyways, how many moles of HCl are in 3.722 milliliters of a 1.234 capital M HCl solution? Your turn. Oh, it warms my heart to see everybody working on their chemistry on this beautiful morning. Remember to use your good buddy, your good friend, unit analysis. Oh, I have to. Remember, unit analysis. And you people should feel real honored because I never bring my siren to a face-to-face class, my whistle. I do other things that are just as good. I'll say, ooh, I haven't done this all semester. So if I were in a class, I'd say, use your good buddy, your good friend, unit analysis. Yes, I can be fun and crazy and in a face-to-face setting too. And when you're done, give me a thumbs up. Those of you who don't have your cameras on, use the emoji. Those of you who don't want to use the emoji, well, I'm just going to start going without you. No, I'm not. All right, I think everybody's done. Let's do it. All right, question is, how many moles of HCl? So what are we being asked to find? Moles of HCl. What are we given? Well, how many milliliters of solution we have. And we're also given this number. As soon as I see the capital M, what does that mean? Molarity. And I can immediately rewrite this as 1.234 moles HCl per 1,000 milliliters. And now I'll use my good buddy, my good friend, unit analysis. This is a key thing I have to start with. If I had a ratio that I could convert it to my answer, what units do I want my answer? Moles of HCl. And now using my good buddy, my good friend, unit analysis, whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And where do I get these numbers? From right here, because I knew this really meant this. So I have 1.234 moles of HCl per 1,000 milliliters. Remember, 1,000 is the exact number. Now, milliliters divided by milliliters cancel out. I'm left with the right units. And now, before I go, notice 4 significant figures. 4, my answer should have 4. So let's go to our calculator. And for those of you in scientific notation, and over here in A1, you'll see this, and I'll let you round that off to 4 significant figures. So I'm going to give you 4 seconds. Well, I gave you more than 4 seconds. How do you round this off to 4 significant figures? Keep the 4, keep the 5, keep the 9, keep the 2. Use the 9 right here in front of the 4 to round off. Is that 4 or less or 5 or higher? And 5 or higher. So the 2 becomes a 3. So that's 4.593 times 10 to the minus 3, or you could round it off like this did already. And we'll come over here. And that's how you do. Oh, let's do another one, but let's do something a little different. All right, everybody see right here, and I'll decode it. How many milliliters of a 2.73 capital M NaOH, which is sodium hydroxide solution, must you use to get 1.75 moles of NaOH? Instead of use to obtain, I could have used that. And I could have also said, how many milliliters do you have to measure out? But you get this feeling. All right, this one, Dr. White's going to do. Then I'm going to have you have some fun too. So what are we trying to find? Milliliters, because that's what we're asked. What are we given? Ooh, we're given this. And we're also given 1.75 moles of NaOH. And what does this mean? Oh, look, capital M. That means molarity, moles per 1,000 milliliters. So what this really means is 7.3 moles NaOH per 1,000, sorry about writing it so small, milliliters. And you should know how to do that. So what's the main number we have to start with? This, 1.75 moles of NaOH. And now if we could convert it, what do we want to get to? Not moles. Yes, I'm right. Dr. White confused himself. I'm unconfused. All right, and what are we trying to get to? Milliliters. And what do we use? We use our good buddy, our good friend. Oh, I'm getting all choked up over it. Unit analysis. Whatever we're trying to get to, the units go on top of the ratio. Whatever we're trying to get rid of goes underneath. And where do we get these numbers? From here. We know for every 1,000 milliliters, there's 2.73 moles of NaOH. And now moles of NaOH divided by moles of NaOH. I gotta drink some water. Hang in there. Cancel out, and we're left with milliliters. And now I can go to my calculator. Remember, 1,000 is an exact number. And oh, Dr. White's in his rut again, 3 significant 3. Our answer should have 3 significant figures. All right, let's try this again. Huh. All right, well, now it wants to work. And round this off to 3 significant figures. Keep the 6, keep the 4, keep the 1. You use the 0 to round off. That's 4 or less. So the answer is 641. So if you need 1.75 moles of NaOH, and you have this molar solution happen to be sitting on the shelf, all you have to do is measure out 641 milliliters of that solution. And that's the beauty of molarity. It is beautiful. Now you know I'm a chemist. Hold on, I changed my mind on something. All right, let me decode it for you. How many milliliters of a 3.333 molar sodium fluoride NaF solution must you use to obtain 0.01256 moles of sodium fluoride? Question mark. And that's your turn. When you're done, give me a thumbs up. Interesting, Erica Michelle. Do you have a copy of that, or does Zoom let you put that into the chat?
Yeah, it does.
Okay. Because I'm rarely on chat because I'm talking. I see a few more people need more time, so I'll give it to you. All right, looks like everybody's done, but before you do that, I got a question for all of you. When I see this, can you see polling number 5 on your screen? Okay, well, I didn't think so, but I can. All right, let's do this. The question is, how many milliliters? So what are we trying to find? Milliliters. What are we given? This. And as soon as I see the capital M, I know I need more room, so I'm going to raise this a little. I know, what does this mean? Capital M, molarity, that's 3.333 moles sodium fluoride, NaF, per 1,000 milliliters. And we're also given how many moles? 0.01256 moles of sodium fluoride. This is what I'm going to start with, because if I started with the other number, I wouldn't get anywhere. And what units do I want my answer to be? Right up here, milliliters. And now use my good buddy, my good friend, unit analysis. Remember, I'm still trying to get the Guinness Book of World Record saying that phrase the most times in one semester in a chemistry class. Somebody counting for me? Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. We're talking about the units. This is milliliters. This is moles of sodium fluoride. And the question is, where do I get these numbers? I come over here because I knew this really meant this. Let me fix up this arrow. That looks bad. But anyways, so when I look at this, I know for every 1,000 milliliters, there's 3.333 moles of sodium fluoride. Moles of sodium fluoride divided by moles of sodium fluoride cancel out because anything divided by itself becomes the number one. And I'm left with the correct units. This is an exact number. Oh, look, this is how many significant figures? 4 significant figures. How many here? Same thing, 4 significant figures. And when you multiply and divide, your answer should have the same number of significant figures as the number you're multiplying or dividing that has the fewest significant figures. So with that in mind, I can now go to my calculator. And if we look here, I get 3.768377. And we have to round that off to 3 significant figures. So I'll let you do that. Time's up. 3, keep the 3, keep the 7. When I say 3, it should be 4 significant figures. Keep the 3, keep the 7, keep the 6, keep the 8. That's my 4 significant figures. Use the 3 to round off. That's 4 or less. So the correct answer is 3.7683. Nope, I wrote it down. It should be 3.768 for significant figures. And if I come over here, that's how much you'd have to weigh out. Now, there are ways of measuring out that amount. You won't find it in a lab at COD, but I've worked in research labs and industrial labs where you can get 1,000th of a milliliter accuracy. Yes, you can. Oh no, I went a minute over. I'm sorry. All right, it's time for a break. Come back at 10:56. That's when your digital watch says 10 semicolon 56. I'll see you in 5. time to call you all back to class. Let's get going. And it works. Hold on one second. Everybody have their microphone.
That deal with problems of the type that we're working with right here. It would really be an excellent idea to practice and be able to do.
There we go. All right, let's continue on with solutions. Now, number 2, I'm going to skip. We just did number 3, sort of, but real life, when you've seen how you can measure out a certain amount of material or a solution, and you use a graduated cylinder. I should bring one up. Maybe Thursday I'll bring one. And you can measure out how many moles you need by volume. Well, how do you get those molar solutions? How do you make one up? Well, in real life, you use a special type of glassware, which is really neat, called the volumetric flask. And let me show you one. Excuse me. Let me log out of here. All right, everybody see this flask that says 10 on the screen to your right? This is called the volumetric flask. And when you measure, you put the solute in here, dissolve it, then put enough of your solvent to get right up to this line, and you have exactly then 10 milliliters of solution. Now, volumetric flasks come in different sizes. Here's a 250, 100, 1,000 milliliter. Usually they're multiples of 5 or 10. And the little ones are really cute, like a 5 milliliter. They're really cute. And you mix it up, and you then pour this into a bottle once you've made your solution and store it. That's called making a stock solution. So let's look at real life. And does everybody see on the screen how many grams NaOH are needed to make, thank you, thumbs up people, are needed to make 324 milliliters of a 1.66 capital M NaOH solution. Now, the first thing is, what are you being asked to find? Oh, by the way, did you notice 10 points? All right, you're asked to find grams of NaOH. What are you given? 324 milliliters of solution, and we're given this number 1.66 capital M NaOH. And what does the M stand for? Molarity. So what that really means is 1.66 moles of NaOH per 1,000 milliliters. Now, there's no way you can go from milliliters to grams. You can't. Trust me, I'm a chemist. How about trust me, I'm a doctor? Actually, I'm both. But what you do need is 2 steps. And step 1, you go from milliliters to moles, which we just did. And step 2, you go from moles to grams, which you learned hopefully for test 2 and haven't forgotten because you'll need it for this test. And let's go somewhere real quick. Hold on 1 second while I open up something. Can everybody see molarity 2-step problem on your screen? Thumbs up, people. Do it again if you thank you. All right. Notice in important information, I also have up here molarity, but 2 steps. Step 1, go milliliters to moles, and then moles to grams. So again, I'm cutting down on how much you have to memorize, which I think is a good thing. So step number 1, I want to go milliliters to moles. Well, I've got 324 milliliters. I want to go to moles of NaOH because that's what we're using. So I'll use my good friend, my good buddy, to convert milliliters to moles. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of, I don't know, I got something in my throat today, goes underneath. And I'll put moles, NaOH, milliliters. And where do I get these numbers? If you go up here, notice molarity of a solution really means 1.66 moles of NaOH per 1,000 milliliters. Now, this is a multi-step, and once again, Dr. White likes to round off at each step, but I'll calculate both in case you're a round off at the end person. So now I'll go to my trusty calculator. And I'll come over here and I'll multiply 324 times 1.66 divided by 1,000. Don't forget 1,000 is the exact number. So 3, my answer should be 3. Let's round that off to 3 significant figures. I'll let you do it first. Time's up. Keep the 5, keep the 3, keep the 7, use the 8 to round off. It's 5 or greater. So that rounds off to 0.537. Did I do that wrong? I think I said that wrong. Let's go back. Should be 0.538, bad Dr. White. And that's step one, because are we done? No, we're trying to get 2 grams of sodium hydroxide. So we've done step one. Now it's time for step number 2. And what is that? That's moles to grams. In this case, well, we just figured out we have 0.538 moles. Moles of sodium hydroxide. We want to get to grams of sodium hydroxide. And how do we do that? We use our good friend, our good buddy, unit analysis again. Whatever I'm trying to get to goes on top units. Whatever I'm trying to get rid of goes underneath. And where do I get these numbers? Well, guess what a nice guy Dr. White is? I am. And let's go back to test number 3, important information. If you notice, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. You had to learn this for test 2, and you'll be using it in test 3. But I'm giving you these things. So again, you don't have to memorize it. So first thing I need is 1 mole, and right here is the molecular weight of NaOH, sodium hydroxide. And that's the sum of all atomic weights. Sodium is 23.0, oxygen is 16.0, hydrogen is 1.01. Yes, Dr. White knows these. This number I know by heart. Remember, when you're adding, you get the same number of significance figures to the right of the decimal as the number that has the fewest, 1, 1, 2. So round this off, and that's 40.0. And now I can go back to my calculator. Well, first I'm going to check. Notice moles of sodium hydroxide divided by moles. And there you go. And now I can go and notice if we round this off to 3 significant figures, oh, look, we get the same number both ways, 21.5 grams. And that's how you make up what's called stock solutions of certain molarity. And remember, you have to do 3 steps. Wrong problem. That's something else from chapter. 2 steps. First step, convert the milliliters to moles. We did that this morning. Second step, convert the moles to grams. You did that for test 2. And now Dr. White's going to let you try one. Now, I'll help you out in case you don't have a periodic table. And you all know how to look this up. Here are the atomic weights for sodium and chlorine. Hint, you need 2 steps. I'll even help you out because you might not, you just learned this. And you can look this up in important information. And there you go. Boy, this molarities and solutions is thirsty work. You're doing real difficult chemistry and you're doing it. Aren't you proud of yourselves? It's not that hard, is it? Might even be fun. Now you know I'm a chemist. If you haven't figured it out by now. Oh, I just realized since we didn't have class on April 1st, you missed all my good April Fool's jokes. I'm unhappy now. So I can't use them. It's not April 1st. I was going to even do the one on April Fool's Day. I'll show you how to make paper into gold. You can't say April 7th joke. I did warn you, humor is bad humor Wednesday. Oh, good news. You only got about 30 more minutes of suffering with Dr. White today. All right. Anybody need more time? I think you do. I see people still ciphering, so I'll be quiet. All right, I think everybody's just about done. But before we do that, a couple important announcements from the management meet. Because I was really swamped and busy yesterday. Later today, I've already written it, but I'll post in Blackboard the lab you'll be doing on either Thursday or Friday for you to download. It's a fun lab. Well, it's chemistry. It should be fun. I'm biased. And that's one thing I want to talk about. Another thing is, don't forget on Thursday or Friday, depending which day you have lab, I'll be doing the gas problem set, and make sure you try it before I do it. Now, because the test is next Wednesday, in a little while, I'll be finishing up all the material for test number 3. Oops, test number 3. And I told you it's Awful Humor Wednesday. See, I don't lie. I'll be finishing up, and I will keep my promise that every test, I will finish the material that I cover in the lecture at least a week before that test. And that gives you time to study and practice and do well. All right. And on Monday, I will be going through the solutions problem set since we're finishing it today. And you'll have all weekend. Isn't it nice to work on the problem set for that? So let's get back to work. All right, question is, how many grams of sodium chloride? Remember, please pass the NACL. So we're trying to find grams of sodium chloride. What are we given? How many milliliters? What are we also given? Let me get my face out of the way here. We're given this and as soon as you see capital M with a number and a chemical formula, that's molarity. Molarity, moles per 1,000 milliliters. So what this really means is 4.44 moles of sodium chloride per 1,000 milliliters. Oh, look, someone was nice enough to write on the whiteboard, you need 2 steps. And those 2 steps are, first one, you convert milliliters to moles. Second step, moles to milliliters. I made a mistake, grams. Sorry about that. So let's get to work. And so we have 5.00, which is 3 significant figures. Why I wrote it that way, as opposed to 500, which is 1 significant figure. We're trying to get 2 moles, and this is sodium chloride. And we'll use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. I'll write those in. And where do I get moles of NaCl per 1,000 per milliliters? A step ahead from knowing that the molarity is 4.44 moles of NaCl per 1,000 milliliters. Milliliters cancel out, I'm left with moles. And now I can go to my calculator. Notice 3 exact number, 1,000 is an exact number. Dr. White's back in his 3 significant figure rut. But first, I better write down the numbers so I don't forget. And this is the number I get. If I round that off to 3 significant figures, it's still 2.22. So I now have 2.22 moles of sodium chloride. Am I done? No, because I'm trying to get to grams. And now use properly written step number 2, moles of whatever I have to grams. Well, I just figured out how many moles. I want to get to grams of sodium chloride. I use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top, unit-wise. Whatever I'm trying to get rid of goes underneath. And where do I get these numbers? 1 mole of a compound equals its molecular weight in grams. And the molecular weight is the sum of all atomic weights. And when I add it up, 1 past the decimal 1, here's my answer, 58.5. Before I continue, moles of sodium chloride divided by moles cancel out. I'm left with grams. So now I can go back. And if you round this off to 3 significant figures, now this one is a gray area. And because I do my numbers on the fly, I didn't realize I came into a gray area. If you round that off, you get 130. Well, that's only 2 significant. Well, how do you do that? I would never put this on a test, which is why I always calculate and look at my answers before I do a test. How would you write 130 to 3 significant figures? This is how. But I would never do that to you. And you get this both ways. And that's how you do it. So you weigh out 130 grams or 1.30 times 10 squared grams of sodium chloride and make enough, add enough water to get 500 milliliters, and you'll get that molarity solution. And that's the usefulness and the beauty of molarity. Now, Monday, we'll do more of these. Let's move on. Have to close the window. All right, we've done our molarity problems. Now, good news, Dr. White has a special gift for you. This semester, I'm not going to do dilution. This will not just put omit. Everybody get that? And when you have a certain concentration solution and you want to make it into another lower concentration, you dilute it. You add some more solvent. And this tells you how to do that, but I'm going to skip that this semester. All right. Switch is on. Now, at certain times you might look at something and say, oh, that's the solution. Well, it's not. And what would be some of those things? How many of you ever looked at a glass of milk or looked at a bottle of ketchup? Now I'm getting personal. Or even a bottle of mustard. I'm getting real personal now. But anyways, you say, oh, look, that's homogeneous, the same throughout. It's a solution. And the answer is, no, it's not. What is a glass of milk or milk? It's called a colloidal dispersion. What's a colloidal dispersion? Well, colloidal dispersion is a dispersion of small particles of one substance dispersed, that's why it's called dispersion, in another. It's homogeneous, but it's not truly a solution because in these mixtures, the materials are not truly dissolved, they're dispersed. Now, this part, number 2, I won't ask you, but instead of using solvent and solute, actually solute and solvent, use disperse phase and dispersing media. Now, what, and this you should know, what are examples of colloidal dispersions? Well, milk is one, latex paint is another, and don't try this at home, but your blood is not a solution. It's a colloidal dispersion. Now in milk, what's being dispersed? Fat molecules and protein molecules in the water. And in blood, the same thing. Also amino acids and proteins, same in milk proteins, like I said. Now, oop, I don't have it here. Oh no, I forgot to write it down. Hold on. And Marissa, the answer is yes. I'll never ask on a test, but you should be familiar. Well, colloidal dispersion is a dispersion of small particles of one substance in another substance. That's really all you have to know. This part right here. Okay? I'll wait while you copy that down.
Thank you.
You're welcome. And as you see, all questions are good questions. Now, let me be subtle. How do you know if you have how can you identify a colloidal dispersion? It scatters light. Now, what do I mean by that? Because in a solution, if I had sugar in here, which I don't, but if I did, or salt, and I made a solution, by the way, Dr. White is a flashlight fanatic, and here I take a flashlight, it goes through. Now, if this were milk, and I took a flashlight, you wouldn't see the flashlight. This is a red one, I have green, white. I think I have about 25 flashlights in my collection. Dr. White, since he was a little kid, liked flashlights, they're cool. My best friend has a bigger collection. He's nuts on them too. Why doesn't the light go through? If I had, like I said, milk, you wouldn't see the light on my hand. You wouldn't see anything. By the way, you can try this at home and you'll see I'm not lying to you, because the particles that are not truly dissolved are just scattered, block the light. And that's how you can tell a colloidal dispersion. And if you want, take a bottle of ketchup, put a light to it, go like this. I don't see anything. If you want to get personal, you can do mustard too. Don't do the blood. Please don't. No. I don't want to get sued. I don't want you getting hurt. But anyways, a colloidal dispersion scatters light. All right, let's move on. And between now and Monday, look around your life and your house and everywhere and think about colloidal dispersions. Now, next thing I need to talk about is boiling. I think you're all familiar with, I hope you all have done it one time in your life, boiled water, either to make tea, coffee. I'm not a coffee drinker. But anyways, you can like it, I don't. But tea, or if you're going to make something where you boil it, like rice or noodles, you boil water. And I think you've all seen those bubbles come up. How do you like that? Bubbles come up, and what's boiling? And it switches on like to 120. Oh, by the way, warning, Dr. White's going to do some artwork. So if you fall off your chair laughing, don't hold on tight. I'm not an artist. All right. What's boiling? It's a special form of what we call evaporation, where you convert liquid, something that's liquid, to vapor, which means a gas state within the body of the liquid through bubble formation. So if I had a pot or beaker of water and was on a hot plate, there's the knob, here's the plug, and you heat it up, all of a sudden you see these little bubbles in here coming to the surface. And those bubbles contain what? Water in a gas form, if you're doing water. Now, what's the boiling point of a liquid? That's the temperature at which the vapor pressure of the liquid, that means the water that's forming a gas here, once it comes to the surface, that gas goes this way, the water. And it is a gas, so you can measure the pressure. And we call that vapor. When you have a gas at a temperature where normally it would be a liquid, we use the term vapor. That's why we call vapor pressure. But don't forget, out here, we have atmospheric pressure. And what does that mean? The boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric or external pressure. I'll never ask you what the boiling point of a liquid definition is, but I'd like you to learn that because that's important. So when you're boiling something, when the vapor pressure equals the atmospheric pressure and you measure the temperature, we call that the boiling point. Now, normal boiling point by definition is the temperature at which liquid boils at a pressure of 760 millimeters of mercury, otherwise known as 1 atmosphere. And generally, this is sea level on our planet. And in Chicago, we're at essentially sea level. So when the weather is right and it's 1 atmosphere, 760 millimeters of mercury, you'll find the boiling point of water is 100 degrees C. Now, if you go to Denver, thumbs up, people. Do you see Denver on your screen? The word, not the city. Oh, bad humor again. If you go to Denver, that's called the Mile High City. And you should know when you go to higher elevations above sea level, the atmospheric, and by the way, hint, I don't have it in red, but you get the message. I'm gonna go a couple minutes, well, I'm on time. At higher elevations, the atmospheric pressure decreases. So Denver is a mile high from Chicago. The atmospheric pressure is lower and the boiling point of water is lower. Now, if you go to the top of the Himalayas, this is shorthand for boiling point of water, is very low. And you should know this. Why? Because you're at a real high elevation, the atmospheric pressure is less. Therefore, you need less energy to make the vapor equal, the vapor pressure equal atmospheric. So the boiling point at the top of the Himalayas is way low. On Monday, I'll tell you more what it is. So you should know this. What should you know? The higher you go, the lower the boiling point. Why? Because there's less atmospheric pressure and you need less energy. I'll say that again. You can look at the video too, but since you're here live, I'll do it again live. How do you know I'm not really a video? No, I'm not. But anyways, if you go to higher elevation, like the top of the Himalayas, the atmospheric pressure drops, Therefore, you need a lower vapor pressure to get the boiling point, and you add less energy, so the temperature is lower. Now, how many of you have ever used a pressure cooker? Dr. White doesn't like them because I worked in high pressure chemistry, and I don't think pressure cookers are safe, but that's my personal opinion. But anyways, in a pressure cooker, it's just the opposite. When you heat it, you have water in there that starts boiling. And because it's trapped, the pressure inside that vessel goes higher, and therefore you need more energy to heat the water to boiling, and that higher energy cooks your food quicker. And that's why a pressure cooker does that. And you should be familiar with that. And I'll say it again. When you go to use a pressure cooker, the water that boils when you heat it up is trapped in there. The pressure inside gets higher. Therefore, you have to heat the water a higher temperature. In other words, if you're cooking it in water, which you normally do have some water in there, put wine or whatever, how you're cooking. And that means the temperature in there is going to be higher than normal boiling water. And that's how it cooks your food quicker. If you were taking organic, well, I'll talk about it later in this class. There's a rule of thumb that the higher you raise a reaction, the quicker the reaction goes. I'll teach that next chapter. And that's how you know about boiling. Now, when you're boiling, there's this important thing, and I've already talked about this, called intermolecular forces. And the key thing here is there's a special type of force. Here it's called a dipole, but the key thing is it's called the hydrogen bond, which I've already talked about. That's the extra strong intermolecular force between hydrogen atom covalently bonded to a small electronegative atom like oxygen, fluorine, or hydrogen. And this is why the boiling point of water works. And that should be N, not T. And I'll talk about it in lab or next Monday, how towels work. If I look at the clock, I finished it. I kept my word. We have finished everything for test number 3. On lab tomorrow and also on Friday, I'll go through boiling again because I sort of rushed through it. I'll go through it again. And don't forget, tomorrow or Friday, gas problems. Do them before I do. And also next Monday, solution problems. So do them over the weekend before I do. Also next Monday, oh, let me ask, how many of you give me a thumbs up would like me to do a review for the next test next Monday? All right, by popular demand, I will do my world famous review for next test, test number 3. Ooh, the fingers are working again. But anyways, with that, wow, we had a busy day. I'll say, Gang Gesund, goodbye, be healthy, and don't forget, I have my office hour tonight if you need any help, and you can run away now. It's done with Dr. White's awful humor. Oh, wait a second. Gabriella, do that again. How did you do that? Magic hands.
Oh my God. It's my twin sister. She's watching along as well.
All right. Well, I'm gonna have to charge you extra. What's your credit card number? Everybody, I'd like awful humor Wednesday.
Mm-hmm. Have a
I
good
don't
one,
even charge
doctor.
extra for that. Am I nice? Am I nice? Just think how much you'd have to pay to go to a bad comedy club.
Yeah.
And you can see an instant replay on the video.
Right.
For sure. Have a good one.
I do, I will, and you too. Everybody, you're welcome. I'll see you either Thursday or Friday. Again, Gang Gesund, be healthy. Remember, we're not done yet with the pandemic. Wear a mask because there's some nasty stuff floating around there now. And it seems especially attacking people at your age. I've already had shot number 1. Next Tuesday, I get shot number 2. And even after that, I'm still going to be careful. So with that, gang gazoon. Bye.